Hey guys, it's Mr. Ross. We're going to go over how do you make a new type of graph that we haven't really gone over. You guys may have seen it on some of the worksheets, and I just kind of keep saying, don't do that, don't do that, we're not there yet. But we're going to do a quick review of some of the stuff we have learned. And again, we're in constant velocity, just learning about how constant velocity works and some of the ways that we can represent it. So we started out, and we had this kind of a graph right here. This is what we call a position versus time graph. On this axis is position, so these are increasingly positive positions, and then this is time, so time passing, and then here is zero position and zero time. And if you take a look at this object, the way I would describe it based on this graph is object starts at zero position, so we always have to say what position it started with. Moves at a constant positive velocity, okay? Constant because it's a straight line, and positive because that line is sloped up in the positive direction. It's gaining position. All right. Then the object stops. So this flat portion is where it stops. Okay. So as time is passing, the object is neither gaining position nor is it losing position and going in the negative direction. And then the object moves at a constant negative velocity that is slower than the speed before, okay? I know that that is a slower speed because this is a steep line, this is a fast line. So if you had something, let's say that that's the positive direction over that way, you have something that's going like that, and then this, okay? So it's going fast in this direction, stopping, and then going backwards slowly, okay? All right, now another representation that we had was the motion map. So if you take a look up here, same thing. It started at zero position. Here's zero position, t equals 0. Goes at a constant speed in the positive direction for some amount of time. You could have had like 3 arrows here. You could have had 100. It doesn't matter, but we've got 2. Then it stops. So it stopped for 1, 2 seconds, from 2 to 4 seconds. And then it goes in the negative direction at a constant speed. Bump, bump. Okay. So these are all the representations that we have so far. Again, we could take the graph and we could make some equations out of it for the different portions of motion. But what we're going to take a look at now is the velocity versus time graph. Okay, remember, this graph is position versus time. This is what the velocity versus time graph looks like. It's a little bit different because you have both a positive and you have negative velocity areas. So velocity is going to be our dependent variable. Okay, here's zero velocity right here. Everything going upwards is a positive velocity, and everything going downwards is a negative velocity. So if I was trying to graph this one, and I'll do it in a different color so you guys can hopefully see stuff here. When I looked at this first graph, I started out by saying the starting position. You cannot tell position from a velocity versus time graph. You can tell some other things that we'll cover here in just a little bit, but you cannot tell the actual position. So what we just need to look at is what's the starting velocity. We said a little bit ago that the starting velocity is a positive starting velocity, okay? So we're going to go up into the positive land, and I'm just going to put a dot right here. You don't have to do dots. You can do lines, but I'm just showing you kind of the first position here. Did the velocity change in this first section? No, it did not. So as time passes, we have the same velocity. So we're going to have a line segment that is just flat. Now on those prior graphs, we said that a flat line means it's not moving. Here, a flat line means we're not changing our speed. Okay, so we have a constant speed. All right. So that corresponds with this section right here. In fact, I'll draw these dashed lines again so you guys can see what corresponds to what. Okay, so section 1, section 1. Now, the next portion of this motion was the object stops. Okay. Oh my goodness. I think Mr. Bartos is calling me to get in here, but I've got to finish this video. The object stops, okay? So right here, what would stop motion be velocity-wise? Stop motion would be zero velocity, okay? So for a section of time, we have 0 velocity, okay? The next portion, this guy right here, we have a negative velocity. So we're going to be down here in negative velocity territory. Negative velocity is going to be, let me rephrase that. This negative velocity is slower than what we had before because it is a more shallow slope. So we're going to go over here. We don't want to go all the way to the extreme that we did up here, okay? We want to go a little bit less because it's going slower. So constant speed going across like that. So this is the velocity time graph that we would have that corresponds with this and with this. Okay? So the velocity versus time graphs show us the changes in speed. We use these eventually to kind of figure out things like acceleration. If an object were to change its speed, so let's say that it's starting at 0 velocity and it's increasing its speed to like some kind of positive velocity. Here's what that would look like. Okay? So on a velocity time graph, if you have a sloped line, what that means is some kind of an acceleration. Acceleration is a change in speed, okay? I told you that you cannot determine the position of the object based on these velocity time graphs, but what you can do is something a little bit different. I'm going to put some numbers on these graphs for a second. So we're just going to say this is 2 seconds, this is 4 seconds, and then this is 6 seconds. We'll say this is -1, this is +2. What you can do is if you find the area of the graph in between the 0 line and wherever the graph is. So if I find this shaded area, it's a 2 by 2. So that's +4. +4. All right. And if I find this shaded area, it's 2 by 1. Okay. So it's a 2 by 1. That's a -2 though, because I had a negative velocity. If I add those together, +4 and -2, what that ends up giving me is +2. Now, what is that +2? Well, let's take a look here. This was velocity, okay? So meters per second. This dimension is time, so we're multiplying it by seconds. Meters per seconds multiplied by seconds, you have this is going to cancel this guy out, and we end up with meters. So that 2 was 2 meters. So what you're actually doing when you find the area of these graphs is you're finding how far the object has traveled total from its starting point, okay? Again, we don't know where the starting point was, but we know how far the object has traveled total. Again, if it's a sloped line like this, you can just find the area of a triangle, 1/2 base times height, and you can figure out how far this object has gone. That's when these really get useful, is when you're doing that kind of stuff, so for the acceleration. All right, what I want you guys to do is I want you to attempt the assigned velocity versus time graphs. We're going to go over them when I come back next week, and we'll talk to you later. Okay, have a good one.